welcome to another module in this massive open online course. So, we are looking at the capacity of the Gaussian channel, correct. We are midway through the derivation of the capacity of the Gaussian channel, a communication channel which is basically characterized by the addition of white Gaussian noise to the input, alright. And we have shown that the maximum, so we are looking at the capacity of the Gaussian channel, correct. And what we have seen is that the capacity of the Gaussian channel, when you maximize the mutual information, it reduces to the following thing, that is we have to, it reduces in turn to maximize over the set of all probability density functions. Well, if you look at what we had written, over the set of all probability distribution functions of the output y such that the power is limited, this is less than or equal to sigma tilde square. By the way, this sigma tilde square, this is equal to noise power sigma square plus p. I have to maximize hy minus, of course, we have a constant which is half log to the base 2 pi sigma square. So, first let us focus on maximizing this part, focus on maximizing the differential entropy of the output y. So, let us focus on maximizing the differential entropy of output y. Now, this is slightly laborious, correct. The procedure for this is slightly lengthy. So, let us go through it, the procedure to demonstrate. So, we are eventually going to show that corresponding to the variance sigma tilde square, the Gaussian probability density function has the maximum differential entropy. However, the procedure corresponding to this is slightly involved and we are going to go through this in a step by step fashion. The first thing we have to do is I want to introduce a concept known as the Kullback-Leibler divergence, okay, and that can be defined as the following. Okay, so we will go through that. First, let us start by considering so consider the following quantity. Okay, it might sound slightly arbitrary, but it is well motivated. It is defined as gy of y log to the base 2 f of y divided by g of y dy, where these two quantities f y of y and g y of y, these are two different PDFs. Two different PDFs or probability density functions for the random variable y. Okay. And now what you are looking at is basically, now if you look at this, we want to use the convexity of the log. Remember, the convexity of the log says that summation, from convexity of the log we have summation pi I equal to 0 to m minus 1 pi log to the base 2 xi. This is less than or equal to log to the base 2 summation I equal to 0 to m minus 1 pi x y. That is, if you look at this, we said that the function always lies above the chord for the log function, that is function always lies above the, this is log 2 to the base x, correct. So, you can see function always lies above the function always lies above the chord, that is the first aspect. Now, the second point here, if you look at it, this is simply, so look at this, this is simply a probability density function, this is a PDF, you can think of this as Pi, you can think of this quantity as xi, and this quantity integral is nothing but a continuous sum. So, one can also write in this case, for instance, one can also write, instead of a continuous sum, I can also consider probability density function p x of x log 2 to the base, correct, log 2 to the base log to the base 2 x integral, correct, or log 2 to the base 2. You can also look at not necessarily the x, you can also look at any function of x. Okay, so you can look at, for instance, any function g of x, and that would be less than or equal to log to the base 2 integral minus infinity to infinity p x of x g x dx. Of course, there has to be a dx here also. Okay. So, basically what you have is you can extend this to a continuous integral, which is a continuous sum. Okay, this is your Jensen's inequality. Remember, inequality for Jensen's inequality for the concave functions, okay, which basically says that the function always lies above the chord. All right. So, what you are saying is that summation, the discrete sum, can naturally be extended to integrals, all right, by replacing the summation by an integral, and the probabilities, the discrete probability or the probability mass function corresponding to the xi's to a probability density function over x. Okay. So, that is the whole point. Okay. And this is the Jensen's inequality for a concave function, and log of course is a concave function, correct. That makes the Jensen's inequality applicable for the log function. Okay. And therefore, now if you look at this quantity that we have, integral minus infinity to infinity, we have g y of y log to the base 2 f of y divided by g y dy. Now, using Jensen's inequality, this is less than or equal to log to the base 2. You have to bring integral, the summation inside the log, g y of y into the argument f of y divided by g y of y times dy, and now you observe that the g y's cancel, and therefore, what we have is this is equal to nothing but log to the base 2. What remains is integral f y of y dy, but this quantity is the area under the probability density function. because Fy is any probability density function this is area under the probability density function. This quantity integral minus infinity to infinity Fy dy is the area under the probability density function. Therefore, this is equal to 1, the total area under the probability density function. Okay, integral minus infinity to infinity Fy dy. Okay, and therefore, this is equal to log 2 to the base 1, which is equal to 0, and naturally therefore, we have the very important and interesting inequality that integral gy of y log to the base 2 Fy of y gy of y dy less than or equal to 0 implies log Fy of y divided by gy of y is nothing but minus of log gy y divided by Fy y. So, this is integral minus infinity to infinity minus gy of y log to the base 2 dy, and this is less than or is equal to 0, and finally, you bring the negative side to that side, that implies minus infinity to infinity gy of y log to the base 2 gy of y, correct, divided by Fy divided by Fy of y divided by is greater than or equal to 0, and this quantity integral minus infinity gy of y log to the base 2 gy y divided by, this is known as the Kullback. This is known as the Kullback-Leibler, okay, the Kullback-Leibler divergence. Denoted by D okay. So, this is the Kullback-Leibler divergence, and this is always greater than or equal to 0. Okay. So, we have shown, so we have defined this quantity, this is known as the Kullback-Leibler divergence, okay, and we have shown that this quantity is always greater than or equal to 0, and we are going to use this property further in deriving the probability density function that maximizes the differential entropy. Okay. So, remember that is our original aim, alright, we have not yet set out to do that, which we are going to do shortly, which is to basically derive the differential entropy. First, find the probability density function y which maximizes the differential entropy corresponding to the constraint that the power is less than or equal to sigma tilde square, right, which we have defined as p plus sigma square. Okay. Now, let us now set this Kullback-Leibler divergence. In this Kullback-Leibler divergence, let us set gy of y as any arbitrary PDF. Of random variable y with expected y square equal to sigma tilde square. Okay. So, this is any arbitrary PDF, and Fy of y we will choose this as the Gaussian PDF with 0 mean, that is 1 over square root of 2 pi sigma tilde square e raised to minus y square divided by 2 sigma tilde square. So, we set Fy of y as the Gaussian PDF mean 0, this is your Gaussian PDF, mean equals 0, variance is equal to sigma tilde square. Okay, so we are choosing two PDFs. So, GYY, let it be any arbitrary PDF, except that remember it has to satisfy the constraint that the power that is expected y square is equal to sigma tilde square, and Fy we are setting it in particular as the Gaussian PDF with mean 0, variance sigma tilde square. Now, let us look at the Kullback-Leibler divergence between these two. Now, if you look at the Kullback-Leibler divergence between these two, or the which is also known as the KL, which is also known as simply abbreviated as the KL divergence, also abbreviated as simply the KL divergence. What you see is we have 0, remember the Kullback we have proved that the KL divergence is always less than or equal to KL divergence is always greater than or equal to 0. So, I have minus infinity to infinity gy of y log to the base 2 gy of y divided by Fy of y dy. Now, if you simplify this, this is equal to nothing but integral minus infinity to infinity gy of y log to the base 2 gy of y dy, that is log to the base 2 gy of y over Fy can be written as log to the base 2 gy minus log to the base 2 Fy, correct. Now, if you look at the first term is nothing but minus the differential entropy of y corresponding to the probability density function g. So, I am going to simply write it as minus h of gy, that is basically differential entropy of y corresponding to the PDF gy. Gy minus integral minus infinity to infinity well gy of y log to the base 2 1 over f of y dy. Now, remember f of y this is the Gaussian PDF. Okay. So, we have, let us simplify this quantity, although we have already done it before when we are calculating the differential entropy of the Gaussian random variable, but of a Gaussian source, but let us do it once again 1 over square root of 2 pi sigma tilde square e raised to minus y square by 2 sigma tilde square 1 over Fy of y, this is equal to, well naturally this will be square root 2 pi sigma tilde square e power y square by 2 sigma tilde square, and log to the base 2 1 over Fy of y is basically half log to the base 2 2 pi sigma square plus log e to the base 2 into log of e raised to y square by 2 sigma tilde square to the base e. So, that will simply be y square divided by 2 sigma tilde square. Okay. So, we have simplified this quantity log to the base 2 1 over Fy of y. So, I have simplified this quantity. Now, I am going to substitute it in that integral and evaluate that. Now, if you look at the previous integral, that will be, when I am saying previous integral, I am saying this. So, we are focusing on this now. Okay. The first integral is there, focus Now on this integral, okay, and this integral is integral minus infinity to infinity gy of y log to the base 2 1 over fy of y dy is integral minus infinity to infinity. Well, gy of y, substitute log to the base 2 1 over fy of y, that is half, apologize for this is half log to the base 2 2 pi sigma square e plus log e to the base 2 into y square divided by 2 sigma square dy, which is equal to, if you look at this, this will be integral minus infinity to infinity gy of y. Well, this half log 2 to the base half log to the base 2 2 pi sigma square is a constant. So, this will come outside half log to the base 2 2 pi sigma square e plus, now again log e to the base 2 is a constant, okay, divided by 2 sigma square is a constant. This will be minus infinity to infinity gy of y y square dy. Now, if you look at this integral minus infinity to infinity gy of y dy, this is nothing but 1. This is the total area under the probability density function by the property of the total probability, correct, that has to be 1. The integral, that is the area under the probability density function, is 1. Now, if you look at this quantity, this is interesting, integral minus infinity to infinity gy into y square dy, this is nothing but expected, I am sorry, this has to be sigma tilde square, expected y square, this is equal to sigma tilde square. Everywhere I have been writing sigma square, this has to be sigma tilde square. Okay, so this has to be, this is also sigma tilde square, yeah. So, this is also sigma tilde square, sigma tilde square, sigma tilde square, and this has to be, and therefore, what we have is half log to the base 2 2 pi sigma tilde square not e. Two pi sigma tilde square, 2 pi sigma tilde square, half log to the base 2 2 pi sigma tilde square plus log e to the base 2 into 1 by 2 sigma tilde square into sigma tilde square, and now the sigma tilde squares cancel, and therefore, what you have is half log to the base 2 2 pi sigma tilde square plus half log e to the base 2, which is equal to nothing but this is basically your half log to the base 2 2 pi sigma tilde square e. This is nothing but the differential entropy of the Gaussian source. So, what we have shown is basically, if you look at this, what we have shown is basically minus infinity to infinity gy of y log to the base 2 1 over fy of y dy, this is equal to half log to the base 2 2 pi sigma tilde square e, which is nothing but d of differential entropy of Gaussian source with variance equal to sigma tilde square. So, we have shown that this quantity is indeed the differential entropy of a Gaussian source with the variance equal to sigma tilde square. And now finally taking this all back, substituting it, this integral we have evaluated, what we have is, if you do a recap, we have 0 less than or equal to, if you just are willing to spend some time, just reflect or go back, 0 is less than or equal to the Kullback-Leibler divergence log 2 to the base, well, f of y dy, this is equal to, well, h of gy, that is the differential entropy of y corresponding to the arbitrary probability density function gy, minus half log to the base 2 pi sigma tilde square e, which means if you, I am sorry, this is minus and this is plus, okay, which means if you look at this, what we get is half log to the base 2 pi sigma tilde square e is greater than or equal to h of g of y for any arbitrary probability density function g y of y such that expected y square is equal to p. That is interesting. So, what we have shown is that for a given variance, okay, for a given, so what if you reflect on this, and we have shown a very important result, if you reflect on this, what you will realize is, what we have shown is that for a given variance, that is, if you consider a random variable with a given variance and mean 0, the Gaussian probability density function maximizes the differential entropy. That is, for a given power, amongst all the sources, Gaussian source has the maximum Gaussian source has the maximum differential entropy. Okay. And now therefore, if you go back to our original problem, that is maximizing, or which is, remember, this is all an aside to derive that probability density function which maximizes the differential entropy. Now, if you go back all the way, remember we have this problem of maximizing the capacity is maximizing the mutual information subject to Ey square less than or equal to, well, sigma tilde square Hy minus half log to the base 2 pi sigma square e. We now know what maximizes this. We now know max equal to, max occurs for the Gaussian source, and max h of y is basically half log to the base 2 pi sigma tilde square e, and therefore, the capacity will be half log to the base 2 pi sigma tilde square e minus half log to the base 2 pi sigma square e, which is half log to the base 2 sigma tilde square divided by sigma square, and we know sigma tilde square equals p plus sigma square. So, we have finally C equal to half log to the base 2 p plus sigma square over sigma square equals half log to the base 2 1 plus p over sigma square. But remember, p over sigma square, remember p is the power of the transmitted symbols x, sigma square is the noise power, therefore p over sigma square is nothing but the SNR. Therefore, we have the celebrated result for the capacity of the Gaussian channel, that is log to the base 2 1 plus SNR, and this is the capacity, this is the, well, this is the very popular result, popular and fundamental, popular result for capacity of channel with Gaussian noise, and also very practically relevant, because as we have said many times before in this course, the Gaussian channel model is one of the most frequently occurring channel models and one of the most popular models to represent or to model the channel in a typical communication system. Okay, so this is one of the most fundamental results which characterize what is the maximum rate at which information can be transmitted over bits per second across a Gaussian channel. Okay. So, this is fundamental result characterizing rate of information transfer in terms of bits per channel. In terms of bits per channel use. Now, there is one small modification for this, not a small modification, but if you want to find the bits per second, if I consider a channel of bandwidth, let us say W, that is we have okay. Now, from the channel of bandwidth W, remember we can have a signal. So, channel is band limited to W, implies from the Nyquist sampling rate, the signal. Now, if you go back to our Nyquist we have that signal is completely characterized by samples at rate 2W, right, at samples at rate 2W, that is a sampling rate, that is the sampling rate. If we have 2W samples per second, that is the maximum number of distinct samples, that is a signal. From the one of the ways to interpret the Nyquist sampling theorem is that if you have a signal that is band limited to W, correct, I can sample it at the rate 2W, and that completely characterizes, and I can reconstruct the signal from these samples. So, the entire signal, so the information in the entire signal is basically embedded in this 2W samples, right, 2W samples per second. So, if I can sample the signal at 2W samples per second, I can basically represent the entire signal, I can capture the entire signal. So, these are the maximum number of novel samples, or these are basically this is the rate at which I can transmit novel symbols or novel samples across the channel. And now we have seen that per channel use you can transmit half log to the base 2 1 plus SNR bits per channel use. Therefore, maximum information rate. So, this is the number of symbols per, you can think of it, number of symbols or samples per second implies maximum information rate the maximum information rate is equal to half log to the base 2 1 plus p over sigma square, that is bits per symbol times 2W symbols per second, and this gives your basically W log to the base 2 1 plus p over sigma square. That is the capacity of the Gaussian channel in, or you can use it as C tilde, that is this is in bits per second. Okay. Capacity in, previously we had bits per channel use, this is, and needless to say this is also known as the Shannon-Hartley law. Okay, this is known as Shannon-Hartley law. Shannon, of course, again I do not need to remind you, we already described him, the father of information theory, from whose fundamental works all these results regarding capacity of various channels follow. In particular, of course, Shannon's work is much more general, provides a framework to characterize the capacity of any general channel. In particular, this result is for the Gaussian channel, and it is very fundamental, it is relevant, it is fundamental in its own right, because as I have told you, the Gaussian channel is one of the most frequently occurring channels, and it is one of the most popular channel models, and also widely applicable in practice. So, therefore, this result, the sub result of the general capacity framework is of fundamental relevance and also very popular. Okay. So, this is a fundamental result and very elegant and simple result, needless to say. So, this is a fundamental result which characterizes the capacity of the Gaussian channel in bits per second. We already said this is the Shannon-Hartley law. Okay. So, in this module we have completed the derivation of one of the fundamental results, that is the capacity of the Gaussian channel, which we have shown is basically in terms of bits per channel use is half log 1 plus SNR, in terms of bits per second over a channel of bandwidth W is W times log to the base 2 1 plus SNR. Alright. So, we will stop here and look at other aspects in the subsequent modules. Thank you very much.